Gauss law that we have been used before to solve the or to find the electric field in the previous example, known as the integral form of the Gauss law. Okay, so the Gauss law, we can also write the law in another form, which is known as the differential form, which we will go through in this. Okay, so here we are going to use the concept of the divergence theorem to change or to rearrange and rewrite the equation from the integral form to the differential form of the Gauss law. Okay, so this is just a review of the divergence of a vector. The divergence theorem. Okay, remember we have this equation before for the divergence theorem, and we already go through that before. And as a keyword here, the divergence of electric field is similar to the flux. Okay, and then it is also for the divergence of electric field. It is defined as the net outward flux per unit volume over a closed incremental surface. Okay, so we have a source, which is a positive charge, and the sink of the electric field, which is a negative charges. Okay, we can also have zero divergence, which we also call as divergenceless. Okay, so it is not a sink nor source, therefore it is equivalent to no charge, or maybe there is an equal number of positive and also the negative charge. Okay, so here this is what we do in order to uh, change the Gauss law from the integral form here that we usually use to the lastly we have over here, this is known as the differential form of the Gauss law. Okay, so here you can see the integral sign, but you cannot see any integral sign at the end of the product over here, where we only have the divergence of the electric field, which is actually an equation of a differential equation. Okay, so here we use the divergence theorem and we write the left hand side of the equation, and then the right hand side of the equation we use this relation, and finally we come to the differential form of the Gauss law. Okay, so here we can still have the electric field, but here we are using the uh, volume charge density. So this is the differential form of Gauss law is limited to the different volume charge distribution. Okay, so but from the left hand side of the equation we can still use the electric field. Okay, so as a summary, here is the differential form of the Gauss law. Okay, so here the limitation, we only can use this to volume charge distribution, as you can see from this part over here. Okay. Okay. So here is an example of using the differential form of the Gauss law. Okay, so here we are given the electric flux density. So D, we are not given the electric field. So if you are given the electric field, you can just convert it back to the electric flux density, or the other way around. Okay, so here we can use the differential form of the Gauss law to find the volume charge distribution. Okay. Okay, so this is the uh, differential form of Gauss law with electric field, and this is when we change it into the electric flux. So here we are opting for this one because we don't have to deal with the permittivity that we have for this form of the differential form of the Gauss law. Okay, so here later on we will use the divergence. Okay, and substitute the D over here to find the divergence for this part of the differential form of the Gauss law, and from there, after you did the divergence of vector D over here, which is the electric flux density, you can get the volume charge distribution. So here we have this one. The first equation of the Maxwell equation is from the Gauss law. Here we have the differential form, and here we have the integral form. And also remember that the relation between the electric flux D and electric field is given by this equation, where this one is the permittivity of material. Permittivity of material. Okay, so this could be any permittivity, but usually for this course we just use the epsilon zero, so which is the permittivity of a free space. Okay, so if you are given different material to find the electric field or the electric flux, then you have to use the permittivity of that given material.